Okay, so we're working in box D here of 7-8. We're talking about the intersection of two planes. And we already looked at some of this stuff in box B. And when we're talking about this in box B, we went over the possibilities that you can have for two planes in space. Our planes can be parallel and distinct, which we know is going to happen if our normal vectors are parallel. And so by checking the normal vectors, that's how we check to see if they're parallel. They can be coincident, which means they're parallel, and their equations are scalar multiples, or they can intersect at a line. Okay? And this is the option that we're going to spend most of our time working on today. So let's jump into a question here where we are given the equations of two planes, and we want to determine how these two things intersect. Now, when it says determine the intersection for them, you want to say, are they parallel and distinct? Are they coincident? Or do they intersect in a line? And if they intersect in a line, you want to find the equation of that line. Now, looking at these two equations here, what are we going to think about first? What's the first step in all of these sorts of problems? Yeah, we're going to check and see if these are parallel. So let's take a look at our normal vectors here. We'll call this plane 1, call this plane 2, and we'll get the normal vector for each of these. So our normal vector for plane 1 is 3, 1, 2. Our normal vector for plane 2 is 6, 2, 4. Are these things parallel? So these are obviously scalar multiples of each other. 2 times that first vector gets us our second normal vector. So these guys are parallel. So we know that they are parallel. We want to know if they're parallel and distinct, or are they coincident? And when we have the two scalar equations, the thing to check is one of our planes a scalar multiple of the other plane? And looking at these two, I think you can see just by looking at them that, yeah, these two things are scalar multiples if k equals 2. So again, 2 times the first plane is going to give us the entire equation of the second plane. So we can conclude with these ones that plane 1 and plane 2 are coincident. Okay. All right. So let's look at a somewhat more interesting example here. Again, same question. Determine the intersection for these two planes. And again, we'll label these plane 1 and plane 2. And we should always check to see if these things are parallel first. Well, let's see. Our normal vectors are 1, 2, 7, and 1, 3, negative 3. Okay. Are these two normal vectors scalar multiples? No, they cannot be, because our x components are both 1, our y components are different. So let's just write out n1 is not a scalar multiple of normal 2. Therefore, plane 1 and plane 2 are not parallel. So if they're not parallel, there is going to be a point of intersection. And our job is to find, there is going to be an intersection, and our job is to find the line, the equation of the line where these two things intersect. How do we do that? Let's start by taking our two equations here and writing them together as a system of equations. So equation 1 is x plus 2y plus 7z equals 4. And equation plane 2 is x plus 3y minus 3z equals 1. What we want to try to do is solve this system. Now what we have is we have a system of 2 equations and 3 unknowns. So we're not going to be able to get a unique solution for x, y, and z. What it means to solve this is we know our solution is going to be a line. So what we're after is, what this means is find the parametric equation of the line of intersection. So what we're going to end up with is parametric equations. X equals some expression, y equals some expression, and z equals some expression. Okay? So we want expressions for x, y, and z. Okay? And these are going to be in terms of parameters here. And because this is a parametric equation, we're going to have one parametric equation of a line. This is all going to be in terms of one parameter, t. So what can we do first? First step is going to be, I haven't organized this very well, so I'll have to put this down here a little bit. First step is going to be eliminate one of our variables from this system. So eliminate one variable. So if we look at these 2 equations here, P1 and P2, which variable is it easy to eliminate? Yeah. So in this case, it'll be x that we eliminate. Sometimes it'll be y, sometimes it'll be z, but let's eliminate x here by subtracting these 2 equations. So we do this subtraction, we get negative y equals, negative y plus 10z equals 3. Okay. Now, remember what we're after here. We're after expressions of the form x equals, y equals, or z equals. So let's take this thing that we have here and step 2, rearrange this to express this to solve for one of our variables. So rearrange for one of the remaining variables, for one of the remaining variables. And looking at this expression here, the easiest one to rearrange for is y. So I'm going to bring y over to the other side, the 3 back to the other side. We get y equals, what do we get? 10z minus 3. So I'll say negative 3 plus 10z. Okay? And this is important enough that I'm going to put this in a bright green box here. Because this is going to form one of the parts of our parametric equation. Okay, we've got an expression for y. So we're a third of the way down the question here. We've checked y off our list. We're done with y. So let's go back to our original system of 2 equations and eliminate y this time. So step 3, now that we're done with y, we're going to eliminate y from the system. Now, if at this point right here we had said instead of getting an expression y equals something, we had gotten z equals, of course we would have checked z off our list and we would eliminate z from the system. So whichever one we're done with is the one that we're going to eliminate here. So we got to come back to our original two equations here, and I'm just going to rewrite them here. 1 and 2, and so this was x plus 2y plus 7z equals 4, and x plus 3y minus 3z equals 1. Okay. And from these two, we want to eliminate y. So let's multiply this guy by 3, this guy by 2, and eliminate y here. So we'll have 3x plus 6y plus 21z equals 12, making sure that we multiply each of the terms by 3. And for our second equation, this becomes 2x plus 6y minus 6z equals 2. And of course, we are subtracting these two equations. So that eliminates y. We get 3x minus 2x is just x. 21z minus negative 6z is 27z. And 12 minus 2 is 10. Okay. And remember that what we want are expressions for, well, we've got our expression for y, we want an expression for x. Let's rearrange this and get our expression for x. X equals 10 minus 27z. And this is important enough to put it in, I don't know, we'll use a red box this time. And we can check off our x expression. Now, why did we do x in terms of z? Okay, we did x in terms of z because up here we did y in terms of z. So we got y equals something, some function of z. Down here we got x equals something in terms of z. So we eliminated y from the system, and we got our expression for x. The last thing we need to do here is we need to come up with our expression for z. And what we're going to do is we're just going to choose z equal to our parameter, t. Okay. Because what does that give us? Well, if z equals t, this expression here for x becomes x equals 10 minus 27t. Our y expression becomes y equals negative 3 plus 10t. Our z expression is z equals t, and there we are. There is the parametric equation of a straight line. So this is the line that is our solution. So this is the parametric equation of the line of intersection. Okay. And if you don't like the parametric equation, we could always put this into vector form. This would be 10, negative 3, 0, plus t times negative 27, 10, and 1. And that's our line of intersection.